Welcome to the 2019 Sloan Sports Analytics Conference Competitive Advantages Talks presented by Ticketmaster. My name is Jill Payne, and I'm a Sloan Fellow MBA student at MIT Sloan School of Management. It's my pleasure today to present our panel, Going Beyond Tracking Data Using Body Pose for Next Generation Analytics, brought to you by Stats. Please join me in welcoming our speaker, Sujoy Ganguly, Head of Computer Vision for Stats, to the stage.
All right. Hi, everybody. Thanks for coming. I know it's a lunchtime talk, so it's great to see so many people here. I'm going to talk to you today about what we believe to be the next evolution in data collection and analysis in sports. So for those of you who don't know, Stats has been around for 38 years. So we founded in 1981 by Bill James and John Doohan, and have been collecting sports data ever since. That includes both structured and unstructured data. So structured data is things like box scores, and unstructured data would be things like tracking data. So tracking data is the XY positions of players on the court. And we started collecting tracking data actually in 1999 via Prozone Amisco, where humans would actually click on a screen and tell you where all the players were. Now that was an innovative solution in 1999, but was not something that could really scale. So in 2008, we had SportView, which was an in-venue array of cameras that you installed, and you were able to track the players optically. We call it optical tracking because you're tracking using cameras. That system then was installed in every NBA venue in 2013, and sort of really saw a quantum leap in the kinds of analytics you could do in sports. So 2012, Kurt Goldsberry did Court Vision, which sort of reimagined how we thought about space in the NBA. In 2013, Patrick Lucy at CVPR presented role alignment, which really changed the way we thought about player roles in sports. And these were really using spatial data, as was Expected Point, which came out in here again at Sloan, which told us about what's a good shot in the NBA. By 2016, we were really starting to think about the temporal aspect of data rather than just the spatial aspect of data. So again, here at Sloan, we had the thin edge, which was doing shot outcome prediction in tennis by using the ball tracking data. So that's single agent. Then at Wisdom, the next year, again, Long Shah, who is a member of our group now, presented sort of play retrieval. So here you're using the actual tracking data to ask, what's similar? Find me similar plays. And that really requires us to understand the temporal aspect, not just the spatial aspect of the data. And then finally, in 2018, I'm highlighting this because I was on this paper, we did Where Would They Go, which was actually trying to predict where players would move. So we're predicting all 10 players in a basketball team, given the first 4 seconds of their play, we can get the next 8 seconds of their motion. And so we really were able to start to unlock a deeper understanding of the game using tracking data. However, there are limitations. First and foremost, even with the in-camera systems, it's still hard to scale. It's hard to scale because you have to install those cameras in all those venues and maintain them, and they're expensive. So places like colleges wouldn't be able to collect tracking data because it's just prohibitive. So only a handful of colleges had systems. These are the very wealthy colleges that can afford for that kind of system. You can't track games that happened before tracking data existed or from before we had cameras installed in the venues, which means some of our greatest players, our greatest plays, have none of this high, detailed, granular data. So no tracking data on Michael Jordan. And it only tells part of the story. So here I'm going to give you an illustrative example. So here we're going to look at a play. We're going to see the player. We should look here because that's where it is. Sets the screen, drive. We get a kick out. And this player, instead of taking the shot, is going to wait. He's going to wait until he's closed out. Then he's going to take a shot, right? And most NBA players don't like to take highly contested shots. Most of them like to take open shots. Most, not all, right? So we missed something. So let's go back to the video, the ultimate source of truth, right? This is the actual record of what happened. So this is actually a stationary camera from the SportView system, and we'll see the same play. So again, sets the pick. We get the drive. We get the kick out. It's a bad pass. Player has to bend over, gather, collect himself, and take the shot. We need something more than tracking to see something like that, for a computer to understand that and digitize that information. And that information is pose. It's the skeleton of the people at every moment in time. If we had that, we would have been able to see that the player bent over, gathered, and took the shot. So pose tells us a more complete story of the game. So again, historically, tracking systems, in-venue installs, arrays of cameras, use that to collect XY data. The future is to generate tracking, pose, and event data directly from the broadcast video. And when I say directly from the broadcast video, and everywhere there is broadcast video, I do mean everywhere.
17 seconds from Game 7 or from championship number 6. Jordan, open, Chicago with...
So AutoStats is kind of like a time machine. Allows us to go back, collect data about all the great moments and great players in history. So how do we do it? Right, it's all great to say that, oh, that would be cool, but how do you do it? So over the last 5-6 years, sort of been a revolution in computer vision technology. So deep learning, which a lot of people have heard about, I'm sure, and kind of gotten sick of hearing about, I'm also sure, has really unlocked the level of detail that we can extract from the pixels, from images. Specifically, for our use case, it's human pose estimation. So human pose estimation means finding the skeletons of people in a frame. This problem was largely solved by Yasser Sheikh's group at Carnegie Mellon University in 2017 in a technology called Open Pose, for which we have the exclusive commercial license to use in sports. I want to highlight it's a commercial license, so if you're a student and you want to work on things like this, you can still go use it, but if you're another company, you don't get to. And the coolest thing is that this technology, like deep learning technologies are really good at, is generalizing. So, you know, it works in football.
Times voted to the world's best 11 of his fellow professional players, stands over it. Royce is right there to touch it to him. Kroos one out, fire over, scores!
It also works in other football.
That may be the greatest catch I've ever seen.
Defense number 39. Penalties decline. Result of the play. Touchdown.
You have to be kidding me.
So this tells us how we do the detections. How do we extract the pose from the video? But detections isn't enough. We need to go beyond that. We need to go to tracking. We need to know that that pose belongs to that person at that time. So how do we do that? That's the next hard problem. So first you have to have video ingestion systems. You have to be able to collect the video, and you also have to be able to cut the video so that you're getting rid of the commercials. You're getting rid of the halftime shows. You're getting rid of all that information. So we're just getting the gameplay part. We need to be able to calibrate the moving camera. As we all know, in broadcasts, the camera moves to capture the action and focus on what's important. Well, that means we have to, in order to figure out where a person is from an image to their real position on the court, we have to calibrate that on the fly, right? Quite challenging problem. Detect players with Open Pose. We have to link those detections together. This is the same problem you would have in any computer vision system, any computer vision-based tracking system. So that's also largely solved problem or a part of a field called multi-object tracking. Detect and track the ball for cases where that's important. We have to re-identify players as they leave and come back into the field of view. So we call this re-identification because you already know who they are, they left. When they come back, you want to know it's the same person. This is a particularly challenging problem in sports, as I'll talk about in a second. We also need to contextualize that data with event detection or action recognition. And then lastly, you need data quality assurance and data annotation tools to feed back into the system, to make the system better. Every time it makes a mistake, you want to correct it. You want to tell the system, this is a mistake, don't make it again. Right? You want to teach. So we have to have raw data collection, AI-based inferencing, or pipeline or engine, we sometimes like to call, and then an active learning module. Okay, so I said calibration was really hard, right? It's moving camera calibration. So how do we solve that problem? So in the simplest way, I won't give too many details, but what we did is we said, well, I have this great advantage in sports, which I have the court. I can see the court. And that's the place I care about. I care who's on the court and where they are on the court. So why don't I just look at the image and just say, tell me what parts of this image are the court. From what parts of the image are the court, I can tell you what part of the court I'm looking at, and that tells me where the players are. But that can be an expensive process because I have to look at the whole image. So you don't want to do that in every frame. You want to do it in key frames. And then you want to use the actual fact that the camera is moving in a nice, smooth way, because camera operators don't like to jerk around. We like to watch nice things. We can interpolate in between using what's called optical flow. Talked about re-ID. So here I'm going to show you an example, so it's a little more illustrative about what re-ID means. So here you're seeing the box is a player that's being tracked, then he leaves. When he comes back, it's the same person. Right? It's this idea of being able to re-identify when a player leaves and comes back into the field of view. And this is particularly challenging in the field of sports because everybody wears the same uniform, or at least everybody on one team wears the same uniform. And typically when this problem is solved by other computer vision communities, they're using things like the fact that the shirt is red and the pants are blue. We don't really have that option. So we had to really develop a way to pay attention to those features that are discriminative of a specific individual, not just the clothing they're wearing. So that was the secret sauce there. If you do all that, you can then get the things like tracking from broadcast, and thereby be able to have tracking where there wasn't before. So in this case, this Oregon basketball game against Boise State. It also means you can track skeletons, right? Because we're using pose to detect where the people are. So we can look at the shooter during a set of shots. So here, Tony Parker take a couple jump shots, which allows us to do things like understand the variability in somebody's jump shot between makes and misses. So this is actually work that we published here at Sloan a couple years ago. Panna Felsen was the first author on this paper. And this is looking at the variability in shooting mechanics of the lineup of death from the first Warriors Championship. Some nice things you see here. So the makes are in red, the misses are in cyan. And you see things like, well, Draymond Green has a lot of variability from his makes and misses, as does, interestingly, Steph Curry. But that Klay Thompson is sort of like a robot. His shot is always the same, sort of doesn't change. It's kind of cool, something, nice to see. If you also have a great advantage of having more than one view of the action, so you have multiple cameras, minimum 2, you can also get 3-dimensional pose. Right? So here we're seeing a pitcher throwing a pitch, track the pitcher in the view, track his 3D motion. Which means you could do things like compare pitches across time. So here we're going to see in gold is the 50th pitch, in green is the 25th pitch, and red is the first pitch. These are all fastballs by the same pitcher. Okay? And we can see this. We can see the variability. And then in this plot, I'm just showing you the variability in the leg motion. So just the velocity of the leg kick and how that's changing for different pitches in the game. Right, which allows us to understand how people either in time are varying or are varying their motion deliberately in order to fool hitters. So again, going beyond tracking really meant for us to be able to do human motion analysis across sports, nope, that didn't show up right. There we go. Across time. And maybe most importantly, at scale. All right. So being that it's a lunchtime talk, I didn't want to belabor the point. So if there's any questions, please. Go ahead.
For the situations where the players leave and they come back, what sorts of information do you guys actually latch on to keep identifying the same player?
Yeah, so that's a good question. So the question was for the player re-ID problem, when they leave and come back, what specific information are we looking at? So one of the things that we do is we don't try to construct features or a priori, but rather we like the neural networks to construct them for us. So the key there was to give them the hard examples. So examples where everybody kind of looks the same and say, well, but they're not. Figure out what's different. And from what we can tell, the system likes, obviously, jersey numbers if it's available. It likes facial features if it can see them. But it will use combinations of those two things to figure this out. So it's not saying, in every frame I have to see the same thing every time. It's trying to figure that out on the fly. So that's the clever bit. So yeah, so it's called hard example learning. You might hear about it in a lot of computer vision or machine learning conferences, is to say, if you give me the hardest versions of the problem, then I can solve them most generally. Sorry, I think that over here there was a question before, yeah?
When you detect players with open pose, you detect players in a pixel screen. Like, how can you map these pixel positions into court properties?
Yeah, so the question was about how we map, basically how do we calibrate the camera? So I'll go back to that slide, and we can walk through this a little bit. So I think I maybe went a little too fast. So here you can see some set of keyframes. And in these frames, we can see very clearly the court, and we know what part of the court we're looking at. So we just asked a neural network, find me the part of the court I'm looking at, right? So segment out that image. Then what we can do is take, in order to find it refined, we can fit to this segmented court just a regular court image and say, well, what warp do I need to get to this part of the court? And because there's no players, there's no special features about that court that I'm looking at, I'm generalizing it, it's able to do this across many, many venues pretty quickly. Does that make sense? Yep. Cool. Yes, in the back. Yeah, that's an excellent question. So the question was, what's the upper bound in accuracy? So this is actually a hard question to answer because we're collecting data that kind of doesn't exist. So we do need to do a more careful motion capture study, so like using a Vicon system to really verify. But we think we're reasonably accurate, I'll say now. I don't know that we're so accurate that if you were trying to make big decisions on whether somebody's putting stress on a leg that it might be accurate enough to say, well, that's a lot of stress and that's not a lot of stress, but it might not be accurate enough to say it's this many pascals of pressure put somewhere, right? It might not be that level of accuracy, but we do need to do for the 3D in particular. So the 2D it's easier to figure out, right? But the 3D, we need that full Vicon system to compare against, and we certainly do that motion study. Yeah. Yes, hello.
Talking about scalability, what would you say is the minimum percentage, maybe frames per second, or quality of camera particularly you need to be able to implement this? And like, what happens, like, for example, if you don't have like the highest quality camera?
Yeah, so the question was about video quality and what's the minimum video quality needed to do the system. So I think right now we're saying we want 720p video, MP4 encoded. I think we're looking at 24 kbps in the encoding rate. So we have these pretty strict requirements. We are constantly pushing the bounds, but of course, as the video degrades, if we go to 480, the quality of work goes down, so we have to do more work to clean that up and make that better. So right now, we're at 720, but we are pushing down. In terms of frame rates, 30 frames a second, or 2997 to be very precise, is the number. Minimum frames per second. We're also seeing how low we can go with that, but right now that's our threshold that we do to say that we're confident that this will work. Yes?
So with this rich data,
So that's an excellent question. So the question was, how do we query this information? It's so much information now. How do we build a query system around this kind of depth of information? And I'll be honest, I think that's an open question, right? This data is only now being collected, like we're just launching this now. So we don't have a guaranteed answer for that. And that's exactly what we're trying to figure out. And so I think doing things like having partnerships with people. So we announced a partnership with the Orlando Magic this year, just early this week. That's all about trying to figure out how do we query this information when you have that much depth and that kind of scale. What's the ways that analysts want to use it, and how do we build out the systems around this so they can use it? But the answer to that is it's an open question that we're solving in this next a few months to a year sometime soon. Yes? There is very much a vision that is very much being done very much right now. So in the first iteration of the system, we wanted to break things up into simple, digestible problems that we could test the efficacy of. And so that's why we took that approach. But you're absolutely right. The motion of the player should predict the motion of the camera, which should make your calibration easier. And so absolutely unifying those two models is very much what we're doing right now to improve our system. So that answer to that question is yes. Yes, sorry. In the hoodie this time, I'll be more specific.
Does it tell you if Mike pushed off?
Ooh, dangerous. We're a Chicago-based company, so the answer is no, he didn't push off. You know, he's fallen down already, just helped him out. Any other questions? Oh, there we go. Yes. This one? Yeah.
So you're tracking the pitcher's technique, but can you also track the batter's swing and their technique and the bat as well?
Yes, so the question was, here we're showing the pitcher, could you do the batter? The answer is absolutely. So because we actually track all the people in the video independently, and they're really tracked, we can just pick the person we want to display. And once you have the 3D calibration for one pair of frames, you have it for everybody in that pair of frames in principle. The bat we don't track right now. It's only human pose estimation. So I'm going to go to this side, then I'll try to come back. We have very little time, so I'm going to get in trouble. So one last question, I think, yeah? The time delay? So how long does it take to process the system? It depends on the context. So if we're taking, you know, depends on the context of the video, the amount of frames. That's the simple answer. So it's not super fast. It's not a real-time system. It's a post-game system. So and I think that's about as much as I'll say on specific SLA times. But yeah, I think we're cut off. So if you have more questions, find me. I'm at the booth outside.